Chapter 21 is going through specifically gas and liquid chromatography. So we're looking at two different types of instruments. One that's a gas chromatography instrument and one that's liquid chromatography. Now, chapter 22 goes into more detail than I'm going to be covering here. So this level of information is what you're going to be held accountable for. So gas chromatography is where we're starting with this video. So gas chromatography is an instrument that, and this is shocking, the mobile phase is a gas. That's why it's called gas chromatography. So the mobile phase is a carrier gas. It's an inert gas. So it shouldn't react with things, is why it's important that it's inert. It's not going to react with your sample. But since the mobile phase is a gas, we also need to get our sample to be in the gas state as well. So in the gas chromatography instrument, the column, which is where the stationary phase is, which is an open tubular column, is in right here, and it's inside of an oven. So we can vary the temperature of this. What we need to make sure that we do is we can only test samples that we can boil, that we can vaporize, that we can turn from liquid into gas, in the temperature range that's allowed in the column. Otherwise, they can't be tested. So you cannot test solid samples. You can test liquid samples as long as they will boil within the temperature ranges of your oven. So what happens is there's gas tanks that we don't see that are attached to the instrument where the gas is constantly running through it. The mobile phase is constantly moving. The stationary phase is in the column inside the oven. And so there is a port to inject your sample. Now, often these are liquid samples that are volatile. So like organic compounds are really common to be tested this way. And so then the liquid compound is added, mixed with the mobile phase, and then it goes through the oven, and then that mixture separates. So the the mobile phase is typically helium, nitrogen, or hydrogen. Helium is the most common and of course the most expensive. So the sample is added here, it goes into the oven where it boils and then mixes in with the carrier gas and goes through the column, which separates it, and then it moves on to a detector. And we'll talk about those in some detail. And then we get a measurement with our chromatogram coming out of that. Okay, so this is just looking at how the sample is added. So the sample is added using a syringe. So like when you get a shot, it's like a syringe. Yeah, but it's not made to poke people. So the syringe, it's got a plunger, so it pulls up the liquid. And the syringe is always, there's like one syringe for the instrument. So it's always conditioned several times with the solvent, with the air. It's cleaned out really well. And then the sample goes through some glass wool, which all that does is just in case there are any chunks of things, it gets rid of them before it goes through the instrument, because solid particles, especially, like dust, those kinds of things, are not going to boil when it gets into the oven. And so then it's going to be an impurity and cause some issues and maybe screw up your column. Okay, so we have to inject our sample into the gas chromatography instrument. Sometimes we have auto samplers, which are things that are set up, they're attached to the syringe. So you use the computer to tell the instrument what sample to put in and how, and it does that. Sometimes if it's old school, you just have to yourself suck the liquid up with the syringe, poke it in a little port, push the syringe down. So with injecting our samples though, because gas chromatography has an open tubular column, that means we need to have a low concentration of sample because there's not very much stationary phase. So we need to have a very low concentration of sample. Okay, so if the analyte of the chemical that we're measuring is more than 0.1% of the sample, we need to do a split injection. Well, we could either do a split injection or you could dilute your sample so that way it's weaker before you enter it into the instrument. But to be fair, often we just do a split injection. So what happens is in the split injection, this has a picture here. You don't have to know all the parts of this picture. We inject the sample with the syringe, but then there's a little compartment that separates out a lot of the sample, only letting between 0.2 and 2% of the sample make it to the column. So basically, you have a split injection for when your sample is too concentrated to go onto the column, but you don't have a way to dilute it. So the instrument dilutes it by just getting rid of most of it, and only letting a small amount go forward. A splitless injection is when our sample is already very dilute, so it's injected directly into the carrier or the mobile phase, and then that carrier gas moves it onto the column and everything happens. We have another scenario, which is the on-column injection, and that is for samples that we don't want them to have a gap between when they are added to the instrument and when they get into the oven. Or I lied, but they can't even go. Um, yeah, we have to very closely monitor their temperature, I guess. So it can't, there's a variation in temperature between the syringe where it's entered and then like it mixes with the mobile phase and then when it gets to the oven. Now there is a way to control that temperature, but it varies more. So an on-column injection puts it directly into the column. So there's not that, it doesn't have this mixing phase. So it's basically, it has to be a splitless injection because it doesn't touch any other part of the instrument. It goes from the column directly to the detector. This is only true when we have things that are temperature sensitive, they decompose. And we have to keep the column temperature very low in this situation. So this is just showing example like pictures of this. The split injection, what we see is all this business going on in the middle. So what it does is it vents out most of the sample. It purges, it releases, it gets rid of most of the sample before it moves on to the column. In the splitless injection, it still goes through the mixing with the mobile phase, but then it goes to the column. And then in this one, the column is right here. So there's like the syringe and there's the end of the syringe needle and there's the column. Okay, so it goes, there's no mixing area for that. Okay, so I'm not going to talk about the column here because the information about the column, which is where the stationary phase is, comes from chapter 21. It's partition chromatography using an open tubular column. So if you look back, that is, so like if we go through the parts of the instrument. Oh boy. I don't know what I did. Bad things. Oh, I got real excited. There we go. Okay. So we just talked about what happens right here. Check. This is from chapter 21. Look at the open tubular column with partition chromatography. Check. So we're going to move on to the detector now, is where we're at. So when we have GCMS instruments. GC stands for gas chromatography. MS stands for mass spectrometer. The GC component, what it does is it boils the sample and it separates it to its components. And then the detector is actually the mass spec. The sample leaves the column and goes directly into the mass spec instrument. So in that case, the detector is a whole nother instrument, the mass spec. And so the retention times, we have the retention times coming from the GC component, but we don't see, but then the mass spec is making the measurement. So this is a very common instrument and it's used a lot when we have samples, especially that we don't know what's in them, like truly unknown, like environmental samples or just unknown things, because mass spec is able to help you identify an unknown compound, where GC, it doesn't help you identify an unknown compound. It can tell you if the retention time is different than compounds that you know, then it's something different, but we don't know what it is, just that it's something other than the things that we do know. Okay. We also can, to help determine with the GC, we can spike a sample, which is to add, it's kind of like standard addition, where we add the analyte on top of the sample. But in this case, I mean, it can be done quantitatively, but in this case, it wouldn't be done quantitatively. And so you would test just this pure chemical by itself, and then you would add a little bit of one of the chemicals you think is inside of it, and then test both of them and look to see how they, what happens. So let's say we have an unknown that it ends up having two chemicals, and this is what the unknown looks like. It's chromatogram. And then if we have an unknown chemical, but then I added some cyclohexane, because I think there's cyclohexane in it, and this is what would happen. That tells us, hey, there is cyclohexane, because I added more of the chemical, and what it did was it made one of the peaks bigger. So that peak is cyclohexane. And if you took Gen Chem 2 at St. Charles Community College, the first lab, the one where you used gas chromatography, you did exactly this to identify which peak was which for an unknown sample. Okay, with spiking. All right, so moving on. So this detector is just saying, oh yeah, the mass spec can be a detector. I'm not going to go through that. That was in chapter 21. But some detectors just on gas chromatography instrument. The most common one is the flame ionization detector, which is FID. It's abbreviated that way more than people actually say the term. So the FID. A thing that drives me batty is when people say it's the FID detector. D stands for detector. So you're saying FI, flame ionization detector when you say FID detector. Anyway, in this instrument, or the detector in this instrument, what happens is the sample is coming out of the column in the gas state and it moves into the detector. So what happens is it is mixed with hydrogen gas and air and then burned. They light it on fire. Okay. And when it burns, carbon radicals are produced. Okay, so what happened was this is just the scenario for any carbon hydrogen compound. Okay, so it doesn't have to be just one carbon and one hydrogen. That's not what we would see, but it would be carbon some number, hydrogen some number. Okay, and then oxygen gas in the air, and then it makes this radical, splits off the oxygen. So what happens is we've got an ion and then we've got an electron. Okay, so these ions and electrons are then going to think kind of the photomultiplier detector back from atomic absorption stuff. So those ions and electrons go from a cathode to an anode and make a signal. Now, only 1 in almost a billion carbon atoms makes this free radical, but it is going to be proportional. So, like, if only 1 in 100,000 makes a carbon radical, well, that's true in all your samples. So it'll still be quantitative that way. And this scenario, the FID, responds mostly to hydrocarbons because they can burn. But if it's something that's a non-hydrocarbon, so it's not made of carbon, hydrogen, oxygens, the FID is not going to work well. It's not going to be flammable. We're not going to see these radicals. So the FID only works for hydrocarbons. The only kind of chemicals you can test in a gas chromatography instrument that has an FID are hydrocarbons. That is what we have. That is the detector in our gas chromatography instrument at St. Charles Community College. Our newest, we have 2 of them actually. Our new gas chromatography instrument was real clever. And the detector is actually something you can remove. So we could buy multiple detectors, and like I can put in the FID when we have hydrocarbons, and I could take it out and put it in a different detector when I'm testing a different sample. So we have that opportunity, but we currently only own the FID. But we're going to look at some other detectors. So thermal conductivity detector is another option. This one is not specific to hydrocarbons. So this opens the door. You can test more things with this. What it measures, it's kind of measuring similar to something like specific heat. Back in Gen Chem 1, the Q equals M times C times delta T. C was the specific heat. It's a constant about how much heat it takes to increase the temperature of 1 gram of the substance by 1 Kelvin. Okay. So with thermal conductivity detector, it measures its thermal conductivity. Just go with that's a property that it measures. And then it's going to compare that thermal conductivity, the thermal conductivity of the analyte with that of helium. And then it's able to, based on that, because of its conductivity, get a measurement out of it. So basically it's measuring the thermal conductivity. Okay. And it gets a measurement based on that. So it would be unique to the analyte, and this is what it looks like. There's no fire. It's the gas goes in and it makes a measurement right here. This is where that thermal conductivity is measured, and then the gas leaves. Okay. I mean, what happens up here with the wires is like where it takes that data and deals with it. Okay. So thermal conductivity works for everything. But FIDs are simpler, and so most people have them, and most people do gas chromatography for hydrocarbons. We also have the electron capture detector. So this is even more narrow than the FID. So FID only works for hydrocarbons. Thermal conductivity works for everybody. Electron capture is very specific. It has to be containing a halogen. So fluorine, chlorine, bromine, iodine. Okay, so what happens is the gas goes into the detector, and then it is bombarded with high energy electrons. So the detector has energy or electrons and it's thrown at it. The electrons are attached to it and then make a current. Like they attach to the gas, make a current, and then based on that current, they're able to make a measurement. But this, again, it's very limited. I've not actually ever used the electron capture detector in my experience. I've just never been in a situation where I'm making measurements of the halogenated containing compounds enough where that is the instrument that's in front of me.